I'm Quincy Huhn. I'm a PhD student under Dr. Ragusa in nuclear engineering. And this is my talk on physics-informed neural networks, specifically with Fourier features applied to radiation transport in heterogeneous media. So kind of an outline of what the talk's going to be about. I'm going to go over an overview of 1D transport with source iteration, go over the PINN's architecture, how we're going to change paradigm and the motivations for this work, and then applications of PINNs to 1D transport, including Fourier features, and then some conclusions and an outlook on the research in the future. So starting with transport in 1D, we're solving the transport equation or the linear Boltzmann equation. It's an advection reaction of angular intensity psi on the left-hand side, and on the right-hand side, there's the external source Q and a angular redistribution, including a scalar flux term, the phi on the right-hand side. And our scalar flux is the angular integration of our angular flux. And we have the boundary conditions imposed where on the left side for the positive directions and on the right side for the negative directions in our 1D media. And our transport equation is using discrete ordinates and angle. So we have a quadrature rule with weights and directions up to a degree n, and our PDE will become discretized in that direction, where we'll solve individually in PDEs for in scalar fluxes, which each scalar flux being the scalar flux at that quadrature point. And then our angular integration becomes simply just a quadrature rule, where we sum the angular fluxes the angular flux by the weights to get to scalar flux. The scalar flux is important to us because it will be what require us to do source iteration. So in our PDE, we'll have time steps L, or source iteration steps L. So on the right-hand side, we lag our scalar flux to be dependent on the previous source iteration, and we solve for the next time step of the next source iteration step to get the updated angular flux. And then our scalar flux simply becomes the based off of the updated angular flux, and we iterate until our scalar flux converges to some tolerance. And so this source iteration method is specific to how our PINNs method will be implemented. So now we can look at the PINNs themselves. So some qualities of PINNs, there's no data required for a PINNs method. It's also a meshless method. And instead of learning based off of some data, it'll learn directly the PDE and its boundary conditions. And one of the key elements of neural networks that we're utilizing for our PINNs is the universal representation power of neural networks, where they can function as universal approximators for any continuous function. Another property of neural networks that we're utilizing fairly heavily is the backpropagation algorithms in neural networks. Now, typically these are used in training to adjust the hyperparameters using automatic differentiation, but we'll leverage them, the automatic differentiation methods, to end up calculating the residual. So, ending up, the key idea for our PINNs are we make our output of the neural network the solution of the PDE and satisfy the boundary conditions. We make the input of our neural network the phase space variables that we are solving over, and then we make the loss function, the error to be minimized of the neural network, the sum of the PDE residual of the governing law and the boundary condition residual. So to do so, we have to be able to compute the derivatives of the solution with respect to the input. And again, that's where the automatic differentiation used in backpropagation comes in. And kind of a zoomed in, we'll be able to take the inputs of the phase space and with the output calculate the residual with respect to the inputs, and be able to calculate the residual, which will then become the loss, where the residual plus the boundary conditions will contribute to the total loss of our PINN. So our motivation specifically in this case, we wanted to investigate the ability of neural networks to learn the transport equation. with the idea that we could later leverage this using the computing power of GPUs to maybe be able to solve these types of problems very quickly. And then if we're able to apply neural networks to the transport equation, then later learn instead a parametric transport equation, where in addition to the input parameters of the neural network being the phase space variables before, we add in the additional parameters, potentially the cross section or other material properties of our problem, modifying the PIN so that it also depends on some parameter, and we now have a quicker model to solve for unique solutions to the transport equation. So if we're now applying these PINs to our 1D transport, specifically, the one important thing to us is the application of Fourier features within PINs. So PINs, in cases where the target function to be approximated exhibits a high frequency or multi-scale features, so very present within heterogeneous problems, PINs struggle quite a bit to simulate those. So PINs are biased towards learning these functions along their dominant eigendirections of their neural tangent kernel, and that's from Perdicaris. And Perdicaris in that same paper proposes multi-scale Fourier features as a method of leading to more robust and accurate PIN models. So instead of taking the input of the phase space X directly, we perturb it by some cosine and sine, where we have a weight or frequency that we sample from a truncated Gaussian distribution given a user specified sigma, and these can this hyperparameter can be varied so that they're multi-scale, so that you can capture the short time dynamics and large dynamics as well. And in addition to these sine and cosine projections, we also keep a certain number of direct X values to pass through. We call these bypass neurons, so that there's still that information entering as well. So that makes our modified PIN architecture look something like this. So we have an input layer, which will input our training locations. We have our Fourier projection layer, which has 128 Fourier features, 64 sine and 64 cosine, as well as 10 bypass neurons. And then in all of our PINs, we have 5 hidden layers, each with 64 neurons and switch activation functions, which is fairly similar to a ReLU activation function. And then our output layer gives us just 1 neuron, which gives us our angular flux for the specified direction. And so in this case, we'll end up having where we'll have for each direction in our angular discretization, we'll have a single PIN to solve that direction. So we have as many PINs as we have directions, and then in order to do source iteration to update and converge the total source, we first train each of those PINs individually with the lagged source term. And for the first 3 iterations, we completely reset our PINs and train them from the beginning to get, once we have the updated source. Then we perform source iterations until the scalar flux converges, as I said before. And we have a method of calculating how many epochs will be needed in each training of each training after the source iteration updates to scale using the size of the error. And so we perform the training on each of our PINs, then get our updated source term, which we then retrain our PINs and update until we converge. So we have 2 optimizers that we use. We use both ATOM and LBFGS. We use ATOM optimizer with a learning rate of 0.001 for only 100 epochs, and then LBFGS we use learning rate of 0.5 for 2,000 epochs. And so for each of our trainings, we will use both of those. And this is with our Fourier features. So there are a couple of problems that we have them applied to. And so this is a heterogeneous problem that contains scattering. So we're taking advantage of our source iteration that's required. We have 8 angular directions, and you can see, well, I don't know if you can see, but the colors, they line up. So we have very good agreement between our angular flux solutions and also in our scalar flux solutions our pins and the finite difference solution are dead on. So we're getting really good results here. And then if we look at how the convergence goes, on the left, there's a plot of a single one of our pins. So for one of our 8 directions in this case. And the orange dot represents the end of a source iteration cycle. So as you can see at the end of a source, after a source iteration, the loss will peak again and converge. And as the source iterations continue, we have less and less epochs to train our model back down with the updated source. And so the orange points don't correspond to the one on the right because the one on the right is the scalar flux error. And you can see as the scalar flux error decreases, once it gets below our tolerance, then we'll have a convergent model. This is our other problem that we have here. It's a much more heterogeneous problem that contains void, very different scattering sources and also cross sections. And again, here with our 8-direction model, we have a very good agreement. So kind of some conclusions and outlook now. So we applied pins to radiation transport for heterogeneous problems. So far, the source iteration is wrapped around a set of multiple pins. And we have a Fourier feature mapping for the input that's required for heterogeneous problems. It does end up being about 100 to 1,000 times slower than finite difference problems, as is the method of pins. But as is often reported in literature, pins are less affected by the curse of dimensionality. So in higher dimension problems, we could find some speed up. We'll have a GitHub up once we have this work published. And then just some kind of outlooks as to what's next. Now, instead of having multiple pins, we would like to include our scattering within the PD residual and only use one pin, where we would have to update our pin architecture. And then there's the possibility of angular refinement per spatial zone. So instead of being fixed to a certain amount of angles within our quadrature, we could have in different zones more angles required, basically as however we desire. And then also possibly looking into enforcing causality in our pin design, where the loss function would then be weighted so that it enforces the capital residual first. I'll go for questions.
Thank you. I have a question. So, you know, the fact that it's much lower than finite difference, this is not a fair comparison because, you know, finite difference is calculated in a solution only on a finite clip.
Right.
You of course with a neural network, it's a meshless method.
Right.
It's also like also infinite resolution, right? And so you know the other thing is that, you know, obviously what you really want is to be able to incorporate data into your
yeah.
The neural network is able to make inference with data, simulate data in a natural way. So that's why it's really gonna make a difference. Not trying to outdo finite difference of finite elements, but actually solving problems that finite difference, finite elements cannot solve. So
right.
You know, if you can find these kind of problems, and I'm sure there are problems here.
Right, there are.
In radiated, you know, that regular domains or unknown boundary conditions or, you know, stuff like that.
Yeah.
Then, but you have data, then yes.
Yeah, and that's where the applications
beyond distance
to the inverse problem become fairly relevant.
Exactly. So that's a general comment. Any questions?
Yes.
Can you go back to the Fourier transform, no, Fourier feature?
Yes.
Do you use Fourier mapping for your data for the first layer?
Yeah. So our first layer is replaced by we in addition to our hidden layers, we now have a Fourier feature layer that maps our input into Fourier space.
Okay.
And that's what allows us to capture the heterogeneous problem, because one of the issues of pins is they're very diffusive in solutions without Fourier features. And so the Fourier features allows you to capture the heterogeneous solutions.
Okay.